All right, so there's three objectives today. First, to describe motion in terms of what's called the frame of reference, displacement, time, and velocity. To calculate actual displacement of an object traveling at a known velocity for a specific time interval, and to construct and interpret graphs of position versus time. And the third one is the toughest for sure, the third objective. So we'll probably get through the first two today. All right, first, frame of reference, a system for specifying the precise location of objects in space and time. So when we're talking about frame of references, we have to consider the fact that we might be on a stationary or moving object. So for example, I'm standing still right now in the front of the room. Okay? So I can say that my speed or my velocity would be zero, right? Because with respect to the room. But if I think about it with respect to the galaxy, well, the Earth is rotating at like 24,000 miles per second. Okay, it's rotating very fast. So technically, you have some velocity if you consider your frame of reference something else. Another example that you guys go through every day if you take the subway. You're on the subway, right? And you're on the train. The train is moving pretty quickly. If you're standing still on the subway, you would say you're not moving, right? With respect to the train. But with respect to the ground, you're moving because you're on an object that's moving along the ground. So frame of reference is the idea that depending on the way you're looking at a problem, you may or may not be moving, or your velocity or your position may be changing or may not be changing. Okay, so frame of reference is very important in physics to understand what we're considering. Okay, what we're considering. Let's see. All right, so let's talk about displacement and its definition. Have you heard the term displacement before?
Yes.
Okay, where have you heard it before? I'm curious.
Boat.
With what? Water in a boat, yeah. When you hear you displace this much water, or you displace a certain amount of fluid. Okay, when you're on a boat, you think about displacement as moving something aside. Now, displacement in terms of physical motion has to do with the difference between the starting and final point. Okay, the literal change in position. So let's do some examples. Can I get a volunteer? Come on up. All right. So Andrew is going to start over by that container right there. Okay? And Andrew's going to walk over toward where I am. So let's say he takes like 6 steps, each of like 2 feet. How far has he walked? 6 steps, 2 feet a step? 12 feet, right? So he's moved 12 feet over here. Now go back. Okay, how far has he moved now? 12 feet, right? Okay, so we consider things, absolute value in a sense. Displacement is different. So when we're talking about him moving 12 feet, that's the distance he traveled. And then back is 12 feet, that's the distance he traveled. But displacement has to do with...
He stayed in the same spot, so there's no displacement.
So technically speaking, although he moved 24 feet in distance, his displacement is technically 0 right now. Because he finished and started in the same position. So again, if Andrew were to walk around the whole room and end up back here, his displacement is still 0. So it's the change in your position over time. It's not the same thing as distance. Okay, again, it's not the same as distance. When it comes to distance, you're measuring the path traveled. Distance is a measurement of the path you travel on the path. So if you travel in this weird, curved path, and then come all the way back to the beginning, you'll have a distance of whatever the length of that curve is. You can measure that using calculus. But your displacement would still be 0. Okay, but if I move from here to here, my displacement and my distance are equivalent. I've moved 3 feet to the right, my displacement is 3 feet. But if I start here and I move 3 feet to the left, my distance is 3 feet, but my displacement is negative 3 feet. So what else do we say about displacement then? How is that different? Those two things. Again.
There's no negative distance.
Exactly. Distances you're thinking about are always positive quantities. But displacement can clearly be negative because you can move in the negative direction. I can move this way and say it's south, and this is negative. And I can move this way and this is north, and it's positive. So displacement has to do with the direction you're traveling, not just the path traveled. Right? Whereas the path traveled, we're looking at distance. Okay? Okay. So, if we write this as far as formulas are concerned, you would say that the displacement is the final minus the initial. Okay? You could put a delta x instead of just x there, We could call this right here delta x. Your book has a tendency to overuse the term delta, so sometimes I drop it. But you could put a delta right in front of here saying the change in position. By definition, again, the change in position is displacement. So that's why delta is there for change. Okay, you remember that from math? That delta means change, right? Like delta y over delta x. How do you what? F stands for? Not food. Final. I stands for? Initial. Okay? That's a good question, Mark. I didn't even say that. So final minus initial. Final minus initial. Alright? Alright, let's go to the next problem. Simple problem to start us off. Very simple to start us off. So, can I get someone to read it for us? Nice and loud, please. Julie, go for it.
The space shuttle takes off from Florida and circles the Earth several times, finally landing in California. While the shuttle is in flight, a photographer flies from Florida to California to take pictures of the astronauts and they step on the shuttle. Who undergoes the larger displacement?
Who undergoes the larger displacement in this case? Again, a space shuttle launches here, goes around the room like 40 times, and ends here. And then a photographer, instead of being on a space shuttle, just gets on an airplane and goes directly here, instead of going around the room 40 times. Who underwent the larger displacement, Andrew?
The same.
It's the same. Why is that?
Because they both end up in the same spot.
Exactly. So, who underwent the larger distance in this case, though? The space shuttle on the astronauts, or whatever, right? Astronauts?
Yeah.
I was going to say. The space shuttle. Okay, so displacement is the same for both of these scenarios. But the rocket or the person in the space shuttle had a larger distance. Any questions on this? Does that make sense? We understand the difference between displacement and distance. Okay, it's a very big important fact here. All right. So as we said a moment ago, we can have positive or negative displacements. So just some samples, okay, of positive displacement. It does not matter where you start and where you end. If you move to the right, we consider that to be a positive displacement. Okay, and look at these three scenarios here. Even if you start, let's say, in this case, you start in the negative range, in the third one, I'll point with the pointer so you can see. So we start at the location of negative 10 on the number line, and we go all the way to positive 6 on the number line. It's still to the right. So we do 6, which is the final position, minus the negative 10, which is the initial. So if you were to find the change in position, it would be 16, because it's 6 minus the negative, which is really plus. Over here, we're showing that no matter what, if you move left, it's negative displacement. It doesn't matter if you start in the negative dimensions or start in the positive dimensions. That has no difference, the starting point. It's a question of which direction do you actually move. Okay, so it's always going to be final minus initial. Final minus initial. Okay. Let's talk about velocity now. Let's talk about velocity. We could say that the average velocity of a particle, okay, of a particle that is not undergoing acceleration, okay, the average velocity is its displacement over a given time period. Okay, since displacement is defined as xf minus xi, we replace the delta x with that, and time is tf minus ti. Now, for time, usually you just give it a duration or an interval. So let's say hypothetically, right? I'm standing here, and I take 1, 2, 3, 4, 5 steps in about 5 seconds. Every one of my steps is almost 3 feet, about a yard if you take a full step. So we go a distance or displacement of 15 feet in 5 seconds. So you take the 15 feet, divide by the 5 seconds, which means I'm moving 3 feet every second. Now, what are the units you're seeing here? Meters per second. Okay, meters per second. In physics, you're always going to be measuring displacement and distance with metric system units of meters. Time is always going to be measured in seconds. During the course of the year, you're going to see me do this a lot. You're going to see me put a bold and bracket on the side. It always means the units. Is that clear? M over S is meters per second. Whenever you see it bolded and you see those brackets, you know that that's referring to the units of the problem. Okay? This is the first formula on your formula sheet. So if you've already saved that in Notability, this is the first one that you're going to learn for the year. Pretty basic. You've seen this before in Algebra 2 or Algebra 1 at some point, where you see like distance equals rate times time. But now we're looking at velocity. Now, what should we keep track of here? If I move this way, right? Say I take 1, 2, 3 big steps. That's 9 feet to the left. What would my displacement really be? Negative 9 feet. So what does that tell you about velocity? Yeah, velocity can be positive or negative. Very good. So let's jot that down. If I move to the left, I'm running with a negative velocity. If I move to the right, I'm running with a positive velocity. It's all a matter of frame of reference. Okay, you could say east is positive and west is negative, as long as you're consistent when solving a problem. Elliot probably remembers this. I talked last year about how we say up is positive and down is negative. But some physics teachers try and just flip that around actually. They call down positive and up negative because of acceleration moving down. I'm not going to do that this year because I think it confuses things more than it helps. But just to get the idea that if you're calling up negative, then you call down positive. If you're going to call this negative, you got to call this positive. So it doesn't matter which way you choose, but you need to be consistent when you're solving a given problem. So if you're calling left negative, the whole problem left has to be negative. If you're calling left positive, the whole problem left has to be positive. But you need to be consistent throughout your problem. Take a minute to try example 2 on your own. If you want to work with the person next to you, that's fine. Feel free to work with the lady or gentleman next to you. Bad timing, John?
No, you probably.
So I recommend whenever you do these problems, you list the givens first. So list T equals, list V equals, okay? And then you're trying to find X, you're trying to find that displacement. Because of the units that we've been using all year. Careful of your units. Some of you are noticing it already. Very good. That's 7. Yeah. It's not decimal.
Okay.
So maybe you should convert this to seconds and then add that. Yeah. Correct. It's solving the correct way. So it's how you solve the correct You always say starting time is 0. Guys, you always think of starting time as 0 because you're given like a full delta t there. You're not given TF and TI. Okay, you're not given those values. So think about the starting time as 0. That's the overall duration of the problem. How do you set it up? Okay. I'll give you a little starting point. So we start with our formula like this. Oops. Okay, that's what we had on the last page. It said XF minus XI and TF minus TI. You can just simplify by using deltas. That's what changes, right? And your goal is to find delta x. So you need to rearrange this formula to solve for delta x.
So you're doing negative velocity or something, and then
You're given the velocity, see?
Yeah.
6.02. You're given the time, and you're trying to find the displacement, delta x. Yeah, it's not a decimal. You can't use decimal.
Exactly, that's what I'm saying. So would it help if you put it in seconds?
Yeah,
directly?
very good. Absolutely.
So,
Cooper. Looks good to me. Looks great. I think it is. I don't have the number in front of me. But your work is all correct. Very good.
that's your time, so you convert it over.
I'm just confused as to where the numbers plug in.
Okay, so you're told that the average velocity is 6.02. That's your V, right, for velocity.
Okay.
And what does T stand for?
Time.
So, and you're given a time, right?
So then it'd be
But it's hard to
2
plug.
minutes,
How do you plug that in? What do you have to use? What kind of units?
seconds.
So maybe you want to convert 2 minutes into seconds.
137.
There it is. That's your time. And now you need to find delta x.
So time would be original 0, I guess, minus.
Yeah, so you're
I can just put the second.
exactly. You're given the delta. You're given the whole thing. There is no TI.
You subtract it because your initial starting is 0. Yeah.
That's what we got.
That's what Cooper got. Yeah, it looks right.
but one
And her work was right.
I know but no,
I'm ready.
the way you showed it with the because after you told us to do it like this, but I thought it should be divide because this is technically a numerator.
Well, you're trying to get delta x by itself, aren't you? So
okay.
it's currently divided by 137, so you multiply. But the units are not right there.
What the answer saying is 24 seconds.
No, that's what I'm saying. Your units are not correct. Yeah. All right, I'm going to go over this. I'm going to go over it. I try to give you guys a few minutes to do it, and then I'll go over it. So here, first, we look at this kind of a problem, and we think to ourselves right away, we're trying to find the overall displacement. I don't know where this person, Janie, started or ended. I don't care. All I care is about how far they go. So for example, I could start here and take one step, and my displacement is 3 feet. Okay? My initial and final, it doesn't really matter right now, but I know it's 3 feet. If I take another step, my displacement there is 3 feet. Doesn't matter what the final and initial are, we're trying to determine delta x. Now, V bar means average velocity. You're given that in the problem. 6.02 meters per second. How do I know this is velocity? Because of the units. That's why I told you on the last slide, meters per second represents velocity. The minute you see units of meters per second, you need to think velocity. Okay? Next. It also said it, absolutely. No. I pick random names, relax you. So, close. 2 minutes and 17 seconds. What is that? Would I leave it like that? Good. Be careful. Please don't write 2.17. Okay, that's a common mistake you'll see, thinking 2.17 as a decimal. But there's 60 seconds in a minute, so it's really like 2 minutes and 17 sixtieths of a minute. You wouldn't put it in minutes. Put everything in seconds because your velocity is in meters per second. Whenever you have a velocity in meters per second, your time needs to be in seconds. Okay, so we know those two values. So what I do is I start with this. I list my givens. Where am I getting 137? Who could explain that? Ian? Yeah, so 2 minutes is 120 seconds, plus the other 17 seconds, making 137 seconds. Now, there are two ways this year that you can go about solving these problems. You could just plug in at this point, right? Plug in for V bar, plug in for this denominator delta t, and solve for the numerator delta x. I recommend that you solve generically though, meaning solve the variable equation first, then plug in. So here's what I'm saying. In this equation right here, I'm trying to figure out what delta x is. Agreed? Delta x. And currently delta x is being divided by delta t. How would I get rid of division, Jack? Multiply. So let's multiply both sides by delta t. We're going to do this all in variables. So on the right-hand side, those cancel. And I'm left with delta t times velocity, or average velocity, is equal to my displacement. Okay, change in time times velocity equals change in displacement. And at this point in time, no pun intended, but at this point in time, plug in your time and plug in your velocity. Okay, plug in your time with units, please. So our time is 137 seconds, and our velocity is 6.02 meters per second. Who can tell us why it's important to include the units in the calculation? Sarah.
And then units of t.
Exactly. You know, of x, yeah. Of the answer, I was thinking you were saying. Take a look. Units are seconds. The units of seconds in this denominator, what's going to happen to those units of seconds? They cancel, leaving behind what unit? And you need to be meters because you're looking for displacement. And displacement is a length. So it's measured in meters. I almost said it's a distance. It's not. It's a length. Okay? So when I multiply, unit in the numerator cancels with unit in the denominator. So in the end, I'm left with just meters. And that makes sense. What was the number we got here, Dirks? What'd you get, 8?
I got 8.7.
Give me a nearest tenth. 824 point?
8. Sorry, 0.7.
All right. Do others agree?
Yeah.
Okay, so again, this is a very basic problem, but because you're new to physics this year, what we're seeing is that there's a lot going on. We have to solve formulas with all variables. We have to include our units, cancel properly, come up with the correct units. So although in terms of like the rest of the year, you're going to see like this is easy later in the year. In the beginning, it's going to seem like it's new. Okay, so you need to practice this stuff. So practicing solve generically. So when you're doing your homework problems, okay, you want to make sure that you're solving formulas the way we're solving them. Okay, solving them like this, right here. That's how I like to see them. And then plug in numbers. Now, again, if you decide to plug in numbers here and then solve, it's okay. It's not wrong. I'll still give you credit. It's fine. But I'm just telling you now that I'd rather you do it this way, and there's less room for error if you do it this way. Because you can see the cancellation of the units. Okay, when you solve that way, you can see how the units cancel. Whereas the other way, you might not see that unit cancellation. Okay, so I recommend solving generically, then plugging in the specific numbers pertaining to that problem. Okay, pertaining to that problem. Questions? Scroll down, sure. Okay, let's go to the next slide, folks. So, now that we've talked about displacement, we've talked about velocity, we've talked about distance, what is the deal here with velocity versus speed? Can anybody take an educated guess and extrapolate what I'm going to get at here? The difference between velocity and speed. Johnny, go.
Isn't speed relative to like a plane? Velocity is the speed at which you're moving. Isn't the velocity of a plane lower or faster than their ground speed?
Oh, you're using the terms interchangeably, but that's not what it's referring to. Good idea. No, yes, easy. Good. I'm glad you took an educated guess there. What you're saying, I understand, but that's not what we're looking at the difference here. Please, guys, please give answers. That's what I want. That is good. Peter.
The velocity and speed multiplied equal mass.
No? Good guess, though. Good guess. I'll give you a hint. How about this? I'll give you a hint. What was the difference between displacement and distance?
Distance is how far you travel, it's like from one point to another point.
Louder. While.
While like displacement is more like just like slide, like movement from like changing one place to another.
Okay? So, again, distance is the path traveled. Displacement is from one spot to the final spot. Doesn't matter the path you travel. James?
Velocity is from start to the beginning. Speed is wait, so velocity is finished and
Good.
wait,
He's using finish end. That's correct, James. Keep going.
but velocity is pretty much just time, right? Like time it takes.
Velocity is the displacement over time, like we said in the previous slide. You're right so far. What about speed? What's the difference there now?
It's
I'll give you an example in a minute that might help.
I was
Andrew,
gonna
go.
say something similar to like velocity is like overall, like the time it takes you, the speed is like how quickly you're going, just that sort of thing.
You're along the right tracks, both of you, but you're not saying it exactly right.
Velocity has something to do with like increasing speed.
It's acceleration. Acceleration is increasing velocity or increasing the rate of change. All right, here, I'll give you an easy example, right? So, if I were to go around the room, okay, in 30 seconds, and I say the room is like 90 meters, okay, the length around the room is 90 meters, and I traverse that distance, or that distance, in 30 seconds, I'd be moving 3 meters every second, okay, but my velocity would be 0.
Because you're not going back to the same spot.
What is it, Andrew?
You're going back to the same spot.
Because I'm going back to the same spot. Remember, again, watch. I could run around the room sprinting, and in the back here, and I would say, what was my average velocity? It's 0. Because remember, velocity is what? Displacement over time. Speed is not displacement over time, but distance over time. That's the difference. And I know it's really weird. You're like, what? That doesn't even make sense. The speed has to do with the curved path you traveled on, whereas the velocity has to do with the change in position. So if we were to show the analogy or the difference between them, again, ready? Here's velocity. Velocity equals displacement over time. That's what we just wrote in the last slide. But speed is equal to distance over time. Okay, speed is equal to distance over time. Now, an easy example would be if I traveled from here to Philadelphia, okay, my speed or my average speed will definitely be bigger than my average velocity. Why? Again, I travel, I get my car, I go to Philly, and my speed is my average speed of the whole trip is definitely bigger than my average velocity. How come, Cooper?
No, I was going to say the velocity would be smaller because you didn't have it in the same spot, but because you have to get there faster than, like...
Time period's the same.
Okay.
It's only one trip, ready? So watch, here we go. I'm in New York. Here's New York. I travel this weird path. I go south a little, then maybe north. I have to take a certain route and end up in Philly. Okay? I end up in Philly. Peter, why is my speed greater than my velocity for the whole trip?
Because you actually, the distance you travel, or the displacement is traveled, is measured in like a straight line.
Yes.
Distance you
Is-
travel is more than...
So see that blue line there? Isn't that the distance I traveled? What's my displacement though? This is my displacement, that red line right there. So this value here is going to be less than this value right here, clearly. The red line is shorter than the curved path. You learned that in geometry. The shortest distance between any 2 points is a straight line. So your displacement is always really just the shortest distance. So your numerator is smaller on this one for velocity. This numerator, this value here, this displacement is clearly less than the distance. So whenever you travel on a trip or something, your average speed is always really bigger than your average velocity. Unless you travel on a path that is perfectly straight. Then they're equal, aren't they? If I walk from here to here, the speed and the velocity are identical. They're the exact same thing. The minute I curve at all, now I'm traveling at a certain speed that is relatively higher than my velocity. Again, because think about numbers. Put numbers in place. Let's say this is, I don't know how far away is it? 200 miles. Not 500, geez. 3-hour trip, 200 miles. So 200 miles in distance, But the actual displacement from New York to Philly is probably only like 150 miles. So now instead of this, you have 150, but over here, you've got 200. It's the same time period technically. Obviously, it's not, if you really did travel that. But if you look from start to finish, even if you take this curved path, it takes you maybe 3 hours. The time is the same in both equations. It's still 3 hours. Okay, but the difference is, again, that displacement is a direct line from A to B. Distance is a curved path along the way. Julia?
So does the speed have anything to do with like the miles per hour that you're traveling from point A to point B?
It does, and on your speedometer, when you drive a car, the speed that you're currently reading is called the instantaneous speed. It's the speed that you're traveling at that exact point in time. And that fluctuates when you hit the gas and the brake, right? So over a given time period, the average speed you get is really an average of all the speed you were traveling at throughout the trip. Okay? And simply put, you measure it as distance over time, or speed. Okay? Questions on this? It's very important that we understand the difference here between displacement and velocity. Displacement and distance, and velocity and speed. Okay? And velocity and speed. We've got a minute left. I'm going to pause there because the next thing is this graphical stuff, which I'm going to wait on. Okay? Now, remember, slope of a line really indicates its rate of change. So we saw that a minute ago with the motion detector. It's analogous to velocity. When you walk faster, what happened to the steepness?
Got steeper.
It got steeper. The steepness went up. Good. If you walk slower, the steepness went down. If you walked toward the detector, isn't that a negative velocity?
Yeah.
And wasn't the slope suddenly negative?
Yeah.
Okay, so what we can say here is that really, if I have a position versus time graph, the slope of the line is the velocity of the object. Again, slow moving object, faster moving object, not moving, moving back. So this would be a positive velocity. This would be a much more positive. I'm going to put more positive velocity. That's from like B to C there. From C to D, this is stationary, not moving. And from D to E down here, it's moving in the negative direction.
I'm sorry, is that letter Y?
That's an X position. Yeah, sorry. So the idea, again, is that whenever you find the slope, it's the velocity. Now, can we look at that algebraically? Sure we can. How do I find slope? Any graph, generally. Slope? Change in y over change in x. Well, the y-axis is displacement. The x-axis is time. Isn't displacement over time velocity? That's our formula. So if we were to just calculate the slope of this line, we know that it's velocity based on the units or based on what we have here. So for example, let's say that, I don't know, this is obviously 0, 0. Let's say this point is 3, 6, and this point up here is 5, 10. All right? So we have the first 3 points are labeled on the graph there. 0, 0, 3, 6, and then up here, 5, 10. If we calculate the slope, we can clearly see that the velocity is slow here, and then the velocity is greater here. Let's go about doing that though. Oh, actually, I should make that number bigger than 10. Instead of 10, make that 12. Make that 12. Okay, because 10 will be the exact same answer, actually. How do I find the slope between the first 2 points? Cooper? What do you got? Give me the numbers.
Between which ones are?
The first 2 points.
10 minus 6 over 0 minus 0.
Oh, that's a comma. Jeez, I think I see. You're seeing that as a 10, right?
Oh, yeah, sorry.
It's a 0, 0.
Okay, sorry, 0 minus
Looks like a smiley face now with a nose. It's 0, 0.
over 0 minus 3.
Good. Okay, change in y. That was kind of funny, a little bit. Change in y over change in x. So we get negative 6 over negative 3, or just 6/3 or 2. So the velocity in that first segment of the particle is 2 meters per second, because that's the slope of the line. Again, think about it logically here. I've gone from 0 seconds to 3 seconds, and I've gone from 0 meters to 6 meters. So if I look at that formula up here, right, I just remember that it's 6 meters have gone distance over 3 seconds. Well, that's 2 meters per second. It's the same as the slope. Okay, let's look at section 2 now. I'm highlighting it in red. Let's look at that section there. Find the slope between those 2 points, please. Find the slope between those 2 points using your standard slope formula again. What do we got? Give me, send me through the process though, yeah. Give me all the steps through. Kian, go ahead.
So it's 6 minus 12 and 3 minus 5.
All right, I don't know. You can always, I always did bigger minus smaller, but it's up to you guys. A lot of you are doing it this way. Same difference. 6 minus 12 is negative 6. 3 minus 5 is negative 2. Give me a slope of 3. So clearly the second slope is greater, and as a result, the velocity of the particle or the object is greater in the second time period. So again, slope of a line is velocity. Slope of a line is velocity. When the graph is position versus time. So you might want to write like a verbal statement at the bottom of your notes if you haven't done that, just so you know. You could simply say, the slope of a position versus time graph is velocity. Right, Andrew? I hope you agree with me, right? You're focusing?
You said position over time.
And you stop airdropping.
Position over time.
It's position over time. Guys, if you're going to keep calling each other out and you're going to keep doing stuff like that, I'm going to end up just telling you all you can't use your iPads at all. So, don't ruin it for other people around you.
The slope of a position over time is the velocity.
The slope of a position versus time graph is velocity.
Wait. One more time. The slope of a position versus time.
Graph is velocity.
This is graph velocity.
Position versus time graph is velocity. It is done. That's going to be tough to remove though because it's a low. The object's really flat, so it's going to be hard to remove. It's going to be stuck. I need to get like a spatula. Really, I know. Like a metal spatula is the best thing to actually do that. Yeah. I mean, me and Mr. Richroth know about them. I'm kind of trying to show other science teachers how to use them still.
Did you say other scientists?
Science teachers?
Oh.
Scientists.
Take it easy.
All right. Let's take a look at 3 possible lines here. So let's draw a graph. Okay, let's draw a graph that looks like this. So we have the first and the fourth quadrant. It's position and time. All right? And let's say this. I want you to describe what's physically happening. Okay, just describe what's physically happening when I draw one of the graphs.
Okay.
So, we're going to say that object starts here, does this, does this, does this, does this, and then does this. Okay, each piece has something different, so let's go one step at a time. Let's say you break it down. In Algebra 2 this year, you're going to learn about something called piecewise functions, and you're going to get frustrated because they're not easy. But you have to remember that they're actually very important. Piecewise functions are simply functions that are broken into little segments. So you might have like a linear function and then a parabola. And you're going to say, why do I care about this in math? This is why, this kind of stuff. So when you get to piecewise functions, you appreciate what it's actually there for. You're not just, learning how to do it for no reason. So in this piecewise function, from point A to point B, what is happening from point A to point B? Julia?
Velocity is increasing.
No.
All right.
Good idea, though. You want to say that, right? Because you see something going up.
Yeah.
But what is the y-axis? It's not velocity. What is it? What does the x stand for?
Speed.
Not speed. Yeah, the y-axis here is position or displacement, really. Okay, so what's happening? What's happening from A to B? Somebody help her out. Because you made the common mistake. That's fine. It's okay. Jack.
Moving at like a steady pace away from that.
Yeah. You're moving at a steady pace away from where you started. So this tells me I started a little bit to the right of the motion sensor. And this going up, going away means my position is moving further away. So I'm doing this. Ready? That's what's happening, okay? To start. So that's segment A to B. So from A to B, you're moving at a constant velocity away from the origin. Again, from A to B, you're moving at a constant velocity away from the origin.
What if the constant velocity be BC and EF?
That's if this graph was measuring velocity, but it's not. It's measuring your position. If I watch, Julie, ready? From B to C, this is what's happening. Am I moving? It's zero position change. This is position where you're at. It's not velocity. Next time when we do section 2.2, and we're going to do this again, we're going to look at a graph that's velocity there, and then that would be true. Okay? All right, so again, from A to B, we've done this. From B to C, we just what? Stationary from B to C. You're standing still from B to C. All right? What about C to D?
You are sprinting.
C to D.
Sprinting back.
Sprinting, and what are you doing? You're not only going back toward it, but you're going past the origin. So you're sprinting, running through the motion sensor, and ending up over here. Okay? So from C to D, you're moving much faster, but away, well, not away from where you just were, but toward the origin, back toward the origin, and then you're passing through the origin. You could say you're moving in the negative direction. Remember, left is negative. So from C to D, you're moving in the negative direction, thus you have a negative slope. Again, please remember, slope is a measurement of velocity. If your velocity is negative because your slope is negative, it means you're moving this way. That's physically what's happening. Okay, Andrew?
What would happen if there were a detector on like both sides of that thing?
Would it be able to sense them both at the same time, you mean?
Yeah, like they're both on, you like run by it.
I could try it. There is another detector. Wait, let's finish this. At this time, I'll try it. We have some problems I want to get through, though. Or if not, I could look it on my own. But there is another detector. I don't know, Andrew. You'd have to like go like this, though. You just would screw it up. Watch. You'd have to like run around it. You know what I mean? And then this would start picking up the wall, so you'd have spikes in the graph. So I'm not sure if it would work. All right, so from C to D again, you sprint through the detector, end up over there. Now, when you get to this position, do you stop? What happens physically at this position? It's kind of weird, this little corner here in the graph. Little corner. Yeah, but what about it specifically? So I want you to detail, Summer. So I pass the motion sensor. I'm still going this way. What do? Quick turn and go back. We all see that. Remember this flat line from B to C made me stand still a little bit over here? I'm not doing that anymore. I'm not passing the sensor, coming through, stopping, waiting. There's no flat line. So I'm literally sprinting this way and then going like this, turning and coming back. I come back how far? Right to the origin. And then what do? And then I stay there from E to F. Again, I went through the origin, I did a quick 180, turned back. That quick 180 was right here, obviously, the quick 180. I go back to the origin, and then I stand still next to the motion detector. Marco.
Wouldn't the origin be A?
Well, I started off the detector. Remember, A is always the distance away from the origin. That's like your y-intercept, wherever you start there. So if I'm standing here, this gap is like what? Maybe a third of a meter? So that's where that would be. This would be like 0.3 meters up on the graph. Okay? Are we good on this? Do we understand the idea of graphing? So negative slope that we had here from B to C was a negative velocity. I went through the origin, did a 180, came back, and then paused from E to F at the origin. Okay? All right, example 3 let's start with. Let's start with example 3. We're going to go back to our equation. Okay, velocity equals displacement over time. Rachel, read for us, please.
A book is moved on a table around the edges with table dimensions of 1.75 meters times 2.25 meters. If the book ends up at its initial position, what is its displacement? If it completes its motion in 23 seconds, what is its average velocity? What is its average speed?
Okay, so there's a lot of questions here. Still relating to the stuff that we talked about with displacement and distance and how they're different from one another. So, for something like this, who could attack this problem? What do we have? Let's say the starting point is right here, okay? There's the book. We're told that it moves around the edges and it ends up at its initial position. So here's the path taken. Okay, from center to center, I should start there. So what's the displacement? What's the displacement? No displacement. Why?
Ends up same place.
Ends up in the same place. So displacement right now is equal to 0 really. Again, he or she, or the book rather, whatever, moved around the table, came back to where they started, right here. So around the table and back. So no displacement. So is there any average velocity in this problem?
No.
Average velocity is 0 technically, which is tough to think about. Last part though, what is the average speed? Oops. What is the average speed in this case? How do I figure out the average speed?
Alright, you would add the distance that it travels and divide it by 22 seconds.
Good. So remember, speed is the same thing, but we use distance instead of displacement. Okay, so speed, S, equals distance over time. So the overall distance would be 8 meters around the whole perimeter, right? This and this adds up to 4, and then I just double it. So my overall distance is 8 meters over a time period of 23 seconds. So I take 8 over 23, which is approximately a third, a little bit more than a third, right? So we're going to be a decimal of like 0.3 something. With units of meters per second. What does 8 over 23 come out to be?
0.3445.
35 if you round to the nearest hundredth? All right. Meters per second. Okay, meters per second. Meters per second. So, in this problem, how would you graph something like this when it's moving two-dimensionally now? Wouldn't that be kind of weird, right? You would need two graphs separately. You could do it with one graph, but it would be a contour plot. But for moving from here to here, let's say it moves from here all the way to here. Okay, from there to there, it would have a positive velocity. The steepness of the line would look like this. Then it would move down. Now, this is where it gets a little tricky. You need another graph to show that one. But then when it moved back, it would come back toward the origin again. And then the other graph would then move back to its origin. Okay, so if we had, it would look like graphs like this. It'd move away. Okay, then it would kind of pause in the vertical direction, then move back. Whereas the other graph would stay flat for a little while, then it would technically move away, stay flat, and then move back. It's weird because it's two-dimensional, so the graphs look different. But the idea is the same, that you're moving away. In this direction, you move away, then you pause. Even though you're moving this way, you're pausing in this direction, and then you're moving back. That's the first graph there.
So did you multiply the length and width to get to 8 meters?
No. I added all 4 lengths. Perimeter. Distance traveled, right, is the perimeter. 225, 175 is 4. So I just doubled that because there's 2 more sides. Okay? Remember, perimeter is 2 widths and 2 lengths. 2 widths and 2 lengths. Okay. Reader, James, lesson aloud for us.
2 students walk in the same direction along a straight path with constant velocities. One at 1.5 meters per second and the other at 2 meters per second. Assuming they start at the same point and at the same time, how much sooner does the fast getting arrive at the destination is 500 meters away?
So how would you do a problem like this? What would your approach be just by reading it?
It's very fast.
Let's see. 1.5 meters per second. That's like every step is about a meter. So a normal walking pace, well, a big step, I should say, actually. So this is about 1 meter per second, right here. So it'd be a little bit quick, yeah. It'd be like a light skip, not a run, though. I'm not going to go skipping across the room.
Would you have to calculate those speeds and subtract
We'd have to calculate them separately, yeah, absolutely. So we have a bit of a coupled equation or a coupled problem here. We have 2 different parts we have to then combine. So look at student 1, look at student 2. Okay, figure out both of their times and then just subtract the 2. Again, student 1, what's his or her velocity? So we write V1 equals 1.5 meters per second. Student 2 is 2 meters per second. Okay, so there are times where you might have to do problems completely separate from one another and then combine the results in some fashion. Other times where they'll be related to one another. Those are called coupled. assuming they start at the same point and at the same time, how much sooner does the fast student arrive at a destination 500 meters away? So what does that tell me? What's the 500 part? Where's that coming into play? Yeah, but let's use the right term. There it is. And they're both the same, so I don't need to specify here. There's no need to call one of them x1 and x2 because they're both 500 meters, right? So we're trying to find the time it takes the first student, which is going to be more than the time it takes the second student because the second student is moving faster. So find both those times. Go ahead. Make sure you use your formula. You know your formula is v equals x over t. Solve for time in both cases. That's where it gets messy. Okay, solve for time and then get the time for each of them. This is the kind of problem where it's really important to solve generically. So solve this equation for t before you even plug anything in, please. Yeah, of course, because then we lose 1 over t. Straight up again. Negative by itself. You said backwards. But solve generically. Use only variables, man. Please use variables to start. Again, that's the right way to do it. We're trying to solve the variables first. Yeah, correct. Please try and use variables. T is currently down. Trust me, it gets so much easier once you do this enough times. T is down here. I can't isolate T when it's in the denominator. It doesn't work. Please don't divide by x. The common mistake is to try and divide by 500 first. But then you're left with 1 over T. So here's how you start. Multiply by time on both sides.
Okay.
Cancel, cancel. So now your formula reads x equals v times t. But what do I want? I don't want x. Right? I do not want x. That's not what I want. I just switched these two, doesn't it? I don't want x. I want time. But there's something next to time. It's in the way. How do I get rid of it? Divide by this velocity. Divide by the velocity there. Gets rid of the velocities now. And you get t equals x over v. Take a look. From the original equation we had in the beginning, here was the original, right here. What's the only change you notice from the original equation to the one that we have now? What could you have just done?
T and G, just switch.
Anytime, you guys need to look up and focus, please. I know you're in the middle of the problem, please look up for that. Anytime you have something where you have a numerator on one side and a denominator on the other, you can always switch them. It's called the product of the means and extremes in math. So it's like this, ready? You can always switch D and A and it's still true. You could switch B and C and it's still true. Okay, we actually proved that a moment ago, but that's where it comes from. So you can always switch things diagonally when you have a proportion. This is a proportion. This is in my way. This is over 1, right? So technically it's a proportion. If I switch V and T, it's the same as switching this A and D, which you can do. So just switch V and T, that's what you get as a result. So please, as the year goes on, you don't need to solve every time. Just flip-flop, anything like that. Always, because you're going to see formulas in physics. Everything has fractions. When you get to gravity, gravity looks like this. Okay, Fg equals gm1m2 over r squared. You can just flip these two to get r squared by itself. You don't need to go through the algebra once you understand that you can always switch diagonally. Is that clear? So please use that technique, make it easier on yourself. Okay, so that's your time. Now take 500, divide it by whatever rate it was, and you get 2 different times. Okay, just plug the numbers in at this point. Once you solve generically, all you need to do is plug numbers in. I don't know why I use the board when I have the iPad here. Sometimes I forget. All right, so again, the generic solution looks like this. What do I get for my two different times? What do I get for my two different times? King, give me T1.
333.43.
Repeating?
Yeah. And then
333 and a third seconds for time 1. Agreed? And time 2? Time 2, somebody else? 250. Units? So how much faster does student A or student 1 finish, or student 2 finish relative to student 1?
83.3 seconds.
83 and a third seconds. Just subtract the 2. This is the faster student. He arrives after only 250 seconds. The slower student that's running behind takes another 83.3 seconds. So you're really finding like a delta T in a sense. I probably wouldn't write delta because delta usually means final minus initial. Whereas this is really just T1 minus T2 equals 83.3 seconds. Ken?
So then you don't want to borrow the repeating table?
You can, but on the test it depends. I usually just tell you to round to the nearest tenth your final answer. Okay?
So what would that be there? Like,
It'd be 3, because it'd be 3 rounds down, right? So it would just be 83.3. Okay, because the 3 afterward rounds it down every time.
Okay, no, good.
So you have homework in this section. That is due tomorrow. 8 minutes. If you have, anybody have their textbook with them?
I do.
I have a few. I can bring like 2 or 3 in if you want to start on it. But there are 8 problems to do for homework tonight. Okay? No, this is just regular homework. Problem sets are due the day before the first test. Okay? The homework it will say homework 2-1. So you need to have this in your notes, obviously. This should be your last slide for everybody's notes if you loaded your notes. If you do paper, just write it down. The homework will say homework 2-1 is due tomorrow. 2-1 meaning section 2-1. Section 2-1.
homework to do on the iPad?
Homework is due on the iPad, submitted via Dropbox, to my Dropbox folder.
Can you not do it on paper with like pen?
If you really like paper and pen, that's fine. I'm not like it. But you have to turn it to me at the beginning of class. I'm not going to ask for it. I'm going to tell you that now. So for those of you that use paper and pen, if you do homework on paper and pen, before the class starts tomorrow, just either put it on my desk or bring it up real quick. Okay, but I'm not going to say, let me collect homeworks. I'm assuming everybody's doing Dropbox, but if you don't want it, that's fine. But just give me the paper itself. Andrew.
I know you mentioned this before, but what should we title this?
So this should say homework space 2-1 space your last name or initials or something like that. Okay?
Why 2-1?
Because it's section 2-1. Out of your textbook, this is section 2-1.
So homework 2-1.
Okay, like that. If you think you're having issues with Dropbox and you don't submit it or it doesn't go through, it's late. That means that you need to check that it goes through to Dropbox. Are you clear? So you can actually see it in your Dropbox folder once you submit it from Notability. If it doesn't work, you email it to me at the minimum so I know you did it on time at least, and then we'll work out the Dropbox issues. But if for some reason it's like, oh, it's not uploading, I don't care. No excuses. Okay? You email me the homework at that point if it's not going through Dropbox. But get it to me somehow on time. Keep.
We don't do that
No part of homework. Homework's always by yourself. Always by yourself. Okay? If you want to work with somebody and talk about it, that's fine, but I still don't expect to see exact same replicas, obviously. Your problem sets from 2-1 are already online. So if you want to get started on problem sets, that's the ones you can work with a partner on. Okay?
So